Today we're doing an optimization project.
Mr. Stone, maximize our grade. Two light sources of identical strength are placed 10 meters apart. An object is to be placed on point P on a line L parallel to the line joining the light sources at the distance d meters from it, as seen in this figure. We want to locate P on the line L so that the intensity of the illumination is minimized. We need to use the fact that the intensity of the illumination for a single source is directly proportional to the strength of the source and inversely proportional to the square of the distance from the source.
Okay, so we're given that the illumination for a single source, which can be represented by L of x, is directly proportional to the strength of the source. This means that as illumination increases, strength increases, or vice versa. We're given that the strength of the source is inversely proportional to the square of the distance from the source. So, as the strength of the source goes up, the distance from the source goes down. So we could say L of x is inversely proportional to 1 over r squared. R represents the distance from the bulb to point P.
We know that the distance from the left light bulb to point P, which is represented by r left, is the square root of x squared plus d squared because of Pythagorean theorem, which states that a squared plus b squared equals c squared, and in this case, a is x, and then b is d, and then c is r. So you know that x squared plus d squared, and you take the square root of that, is c squared.
And since you're given the total distance from light bulb on the left to the light bulb on the right is 10, you know that this right here must be 10 minus x, because x plus 10 minus x equals 10. So, as Heather mentioned earlier, we're using the Pythagorean theorem again. So the distance from the light bulb to the line L is d, and the distance from point P to the end of line L is 10 minus x. So by using Pythagorean theorem, we find out that the r right, r standing for the distance from the source, is the square root of d squared plus 10 minus x squared. Okay. So given the information we already know, we can say L of x is equal to some constant times the strength over r squared. R squared in this case is the distance from the light bulb to point P. And the constant we know is 1 because the problem explicitly states that the two light sources are of identical strength. Okay. So part A asked us to find the expression for the intensity L of x at the point P. The intensity at point P is represented by the intensity from the left light bulb plus the intensity from the right light bulb, added together.
Using the information we already know, we're able to make the expression. So as Ashay explained, the strength is the intensity from the left light bulb to point P, plus the intensity of the right light bulb to point P. So using this information, we can just use like this equation and plug in the values. So you have L of x equals the strength of the left light bulb over r squared, and we know that r is the square root of x squared plus d squared as found by the Pythagorean theorem, and that squared is just x squared plus d squared, plus the strength of the right light bulb over r squared, which the same thing is found by Pythagorean theorem, which was the r was the square root of d squared plus 10 minus x squared, and when you find the square of the square root, you just get what's inside of the radical, and that's your expression.
Okay, so the formula we know is that L of x equals the strength of the left over x squared plus d squared plus the strength of the right light bulb over d squared plus the quantity 10 minus x squared. We can rewrite this as the strength of the left light bulb times x squared plus d squared to the negative first plus the strength of the right light bulb times the quantity d squared plus the quantity 10 minus x squared to the negative first. So the problem asks us if d equals 5 meters, use the graphs of L of x and L prime of x to show that the intensity is minimized when x equals 5 meters. That is, when P is the midpoint of L. So, for D here, we can simply plug in 5. So we get the strength of the left light bulb times x squared plus 25 to the negative first, plus the strength of the right light bulb times 25 plus the quantity 10 minus x squared, all of that raised to the negative first.
So by taking the original equation that we have, you can find the derivative by using a mixture of chain rule, power rule, and then right in this section right here, we had to use the chain rule inside of the chain rule. So you take the derivative of the outside, which is the 2 times the quantity 10 minus x, and then the derivative of the inside, which is the negative 1, and then you get negative 20 plus 2x, and then you can take out the negative 1 and you get 20 minus 2x.
Okay, so this is the graph of L of x, and we plugged this formula into the calculator, and this is the original. And the question asks, if D equals 5, use the graphs of L of x and L prime of x to show that the intensity is minimized when x equals 5 meters. That is, when P is at the midpoint of L. So we're trying to prove that intensity is minimized when x is equal to 5 meters. So we go to minimum, and left bound 4.787, right bound 5.319, and our guess will be 5, as it should be. And the minimum is at x equals 5. Thus, we know when x is equal to 5, the intensity is minimized. Okay. Now, if we're plugging in L prime of x into the calculator. So, if D equals 5 meters, the graph of L of x and L prime of x to show that the intensity is minimized when x equals 5. That is, when P is at the midpoint of L. So, when we plug in our derivative, L prime of x, we get a graph that looks something like this. We calculate value at x equals 5, and it is at 0. And because our derivative is going from negative to positive at x equals 5, we know that on the real graph, it appears to be something like this. And that is a local min, which means that the intensity is minimized at x equals 5 meters. Part C asks us to calculate if D equals 10 meters, show that the intensity is not minimized at the midpoint. So this distance right here is going to be 10 meters, and we want to show that the intensity is not minimized at the midpoint.
If D equals 10 meters, then when we plug that value into the first derivative graph equals 0 at D equals 10. Thus, we must use the second derivative test in order to calculate whether at D equals 10 there's a minimum or maximum.
Just in case you forgot what the second derivative test is, let me remind you. When f prime of x equals 0 and f double prime of x is less than 0, at that point, that means f of x has a local maximum. And when f prime of x equals 0 and f double prime of x is greater than 0, that means f of x has a local minimum at that point. In this
When you
case,
calculate the second derivative and plug it into your calculator, you find that at D equals 10 there's a negative value. Thus, the original graph is concave down, and at D equals 10 meters there's a local maximum. So we know that at D equals 10 meters the intensity is not minimized.